Many plant systems and processes involve the handling and interaction of solids and liquids. To work safely and productively, operators need to be familiar with the principles related to solids and liquids. Matter is generally considered to be anything that has weight and takes up space. Matter can be visible, like steel and water, or invisible, like air. Matter can exist in three forms: solid, liquid, and gas. Solids have definite shapes and definite volumes. The volume is the amount of space that matter occupies. Liquids have definite volumes, but the shape of a liquid depends on the shape of its container. Gases do not have definite shapes or definite volumes. The shapes and volumes of gases change to match the shapes and volumes of their containers. The terms solid, liquid, and gas refer to the state or phase of a substance. Most substances can exist in any of the three states. For example, water is usually a liquid, but it can also exist as a solid in the form of ice, or as a gas in the form of steam. The state in which a substance exists is influenced by temperature and pressure. For instance, to change water from a liquid to a gas, there have to be changes in its temperature, pressure, or both. Each state of matter has its own unique properties, but before we look at them, let's see how matter is structured in general. All matter is made up of very small particles called atoms. Atoms are made up of even smaller particles. These particles include electrons that revolve around a nucleus. The electrons are negatively charged particles. The nucleus is made up of protons, which are positively charged, and neutrons. Neutrons do not have a charge. When atoms combine with other atoms, they form molecules. A molecule is the smallest particle of a substance that retains all the properties of that substance. For example, one molecule of common table salt has all the properties of salt. A salt molecule contains one atom of sodium, Na, and one atom of chlorine, Cl. One molecule of water has all the properties of water. A water molecule contains two molecules of hydrogen and one of oxygen. The way molecules fit together is referred to as molecular structure. Molecular structure is influenced by temperature and pressure, which help determine whether a substance is a solid, liquid, or gas. Molecular structure is also influenced by cohesive forces that exist between molecules. Cohesive forces attract like molecules. For example, water forms droplets partially because of the cohesive forces that hold water molecules together. In addition to cohesive forces, there are also adhesive forces, which attract unlike molecules. Water droplets will wet the sides of a container because of the adhesive forces between the water molecules and the molecules of the container. That gives you some background on matter and molecular structure. Let's take a closer look now at the three phases of matter. We'll start with solids. As we've seen, solids have a definite shape and a definite volume. Solids retain their shape and volume because of their molecular structure. Each sphere represents a molecule. The molecules fit together in an arrangement called a lattice structure or crystal structure. This one has an orderly geometric shape. Another characteristic of solids is that the molecules are packed closely together compared to the molecules of liquids or gases. There's not as much space between the molecules. The close packing in a solid is a result of the strong cohesive forces between the molecules. The attraction of the molecules holds them together and gives a solid its rigidity and firmness. This crystal represents common table salt. Each sphere is one molecule of salt. If more salt molecules are added, they combine along the edges of the cubic structure, forming a larger salt crystal. The structures of solids range from simple to complex. The exact molecular structure of a solid determines many of its strength and hardness characteristics. Although you can't tell it with the naked eye, the molecules in solids do move. Because of the strong cohesive forces between the molecules, the movement is limited to vibration and spin. In other words, the molecules in solids basically move in place. The molecular structure of liquids is different from that of solids. The molecules of liquids are spaced farther apart, because the cohesive forces of liquids are weaker than those of solids. As a result, liquid molecules move more freely than solid molecules. The ability of liquid molecules to move over each other is what enables liquids to flow. Another characteristic of liquids is that they assume the shapes of their containers. Also, the cohesive forces of liquid molecules are strong enough to hold the liquid together and give it a definite volume. Compared to solids and liquids, gases are made of molecules that are spaced much farther apart. There are practically no cohesive forces between gas molecules, and there is a lot of empty space between the molecules. So, gas molecules move even more freely than liquid molecules. Also, due to the lack of cohesive forces, gases do not maintain definite shapes or volume. In this topic, we looked at the three forms of matter, and we examined the molecular structure of each form. We also looked at atoms, the building blocks of all matter, and learned how they're structured as well. At this point, take a minute to answer a couple of practice questions on this material. Compared to solids and liquids, gases are made of molecules that are spaced much farther apart. There are practically no cohesive forces between gas molecules, and there is a lot of empty space between the molecules. So, gas molecules move even more freely than liquid molecules. Liquids have definite volumes, but the shape of a liquid depends on the shape of its container. Mass is the amount of matter possessed by a body. The measurement of mass is typically expressed as weight. So, the mass of a solid object can be found by weighing it with a scale. The weight of a solid object in pounds is the same as the mass of the object in pounds. In this case, the mass of the object is 2 pounds. The density of an object is related to its mass. Density is the amount of mass in a given volume of a substance. That is, the density is mass per unit volume. As an example, gold has a density of 1,205 pounds per cubic foot. Working out the math, we find that a 1 pound cube of gold has a volume of about 1.43 cubic inches, which is just over 1 inch on a side. In contrast, aluminum is much less dense than gold. Aluminum has a density of only 168.5 pounds per cubic foot. This means that a 1 pound cube of aluminum has a volume of 10.26 cubic inches. At this volume, the cube is just over 2 inches on a side. Density is a property that can help identify different substances that are similar in appearance. Density is also one of the properties that helps distinguish solids, liquids, and gases. In general, solids have a higher density than liquids or gases. A condition relating to solids is stress. Stress is the result of applied forces. These forces can alter the molecular structure of a solid, causing it to change shape. There are basically 5 types of stress that can affect solids: tension, compression, bending, twisting, and shearing. In a way, tension and compression are opposites. Tension occurs when external forces try to pull a body apart. And compression occurs when external forces push on a body. That is, try to push the particles of a body together. Bending and twisting forces are fairly self-explanatory. A bending force tries to bend a body, whereas a twisting force tries to twist a body. Shearing is a stress in which forces are applied parallel to each other and in opposite directions. In other words, shearing tends to make parts of a body slide across each other. These 2 blocks demonstrate the principle, but in reality, a single block would be sheared in 2. Stress works in various ways in plant equipment. For example, compression and tension occur in systems that operate under pressure. Changes in pressure can produce tension and compression. Forces act to pull objects apart or push them together. Bending may occur with a beam that supports a load. The weight causes the beam to bend slightly, but if the load is too heavy, the weight could cause the beam to fail. Twisting stress is predominant in rotating machinery, like the shaft assemblies in motors and pumps. If the twisting stress is greater than the design limits of the shaft assembly, the equipment could be damaged. The weight of a girder applies shearing stress on the bolts. If the stress is great enough, the bolts can be literally sheared in 2. All plant equipment is designed to operate under some stress, but it has to be operated within its design stress limits. If it's not, it's subject to damage. A property of many solids is their elasticity. That is, their ability to return to their original shape after being deformed by stress. Piping systems provide a good example of elasticity. Because they're subject to temperature and pressure changes, piping system components often expand and contract. If the pressure of fluid in a pipe increases, the pipe expands, because the increased pressure exerts a force on the inner surface. We've exaggerated the expansion, but even a small amount causes stress. When the pressure is removed, the pipe contracts or returns to its original shape because of its elasticity. If a pipe is overpressurized, the excessive stress may push the elasticity of the pipe beyond its limits. If the stress is great enough, the pipe could rupture. Solids that are highly elastic will generally yield to the deforming forces of stress. Steel, for example, can withstand a lot of stress before it loses its elastic properties. That is, before it reaches its elastic limit. The elastic limit is the point at which the force applied to a solid exceeds the ability of the solid to return to its original shape. It's the point at which the solid will remain deformed. In a general sense, temperature is the relative hotness or coldness of a substance. But at the molecular level, temperature is a measure of the average molecular kinetic energy of a substance. Kinetic energy is the energy of an object in motion, so temperature is related to molecular motion. In a solid, the molecules vibrate within their rigid structure. The temperature of the solid is determined by the amount of vibration. If heat is applied to a solid, molecular motion increases. If enough heat is applied, the molecular motion can become great enough to overcome the cohesive forces holding the molecules together. The bonds between the molecules of the solid will begin to break down so that the molecules can move more freely. It's at this point that the solid begins to melt into a liquid. Using a common example, when heat is applied to ice, the heat causes the molecular structure of the ice to break down. As a result, the ice melts. In plants, if machinery overheats, the molecular structure of the machine's material may be damaged or weakened. The equipment may fail, or it may continue to operate for a while with no apparent signs of damage. But the operating life of an overheated machine is shortened, so it's important to operate plant equipment within design limits. In this topic, we looked at some of the important physical properties and conditions related to solids. These include mass, density, stress, and elasticity. We also saw how solids are affected by temperature. Now's a good time to try a few practice questions. Mass is the amount of matter possessed by a body. The measurement of mass is typically expressed as weight. A property of many solids is their elasticity. That is, their ability to return to their original shape after being deformed by stress. In a general sense, temperature is the relative hotness or coldness of a substance. But at the molecular level, temperature is a measure of the average molecular kinetic energy of a substance. Kinetic energy is the energy of an object in motion, so temperature is related to molecular motion. Because they can flow, liquids along with gases are classified as fluids. Many fluids in process systems are in a liquid state, so a good understanding of the properties of liquids will help you understand how many systems operate. One of the basic characteristics of liquids is their tendency to seek their own level. In other words, liquids try to rise or fall to the same height at all points. We can demonstrate this with a carpenter's level. It consists of two cylinders connected by a hose. There's an equal amount of water in each cylinder. If we add more water to one cylinder, the level rises in the other cylinder to maintain an equal level. Now, if we pour out some water in one of the cylinders, the level drops in the other cylinder to maintain an equal level. Another important property of liquids is their ability to flow, but some liquids flow more easily than others. The ability of a liquid to flow is related to a property called viscosity. Viscosity is a liquid's resistance to flow. A liquid with a low viscosity is less resistant to flow, so it flows more easily than a liquid with a high viscosity. That's why a thinner, low viscosity oil flows more easily than a thicker, high viscosity oil. The viscosity of a liquid can change with changes in temperature. For this reason, heat is often applied to fuel oil pipes in cold weather. Heat may be applied using electrical conductors under the insulation or small tubes that carry steam. Applying heat to piping this way is called heat tracing. Heating the fuel oil decreases its viscosity and allows it to flow more easily. On the other hand, lubricating oils are often cooled in lube oil coolers to maintain their viscosity and lubricating ability. If lube oil is overheated, its viscosity and lubricating ability are decreased. As a result, it may not adequately lubricate bearings or other components. Another property of liquids is wetting. When you pour liquid out of a container, some of the liquid clings to the walls, so the inside of the container remains wet. Surface wetting is a result of the adhesive forces between the liquid molecules and the molecules of the container. Adhesive forces are molecular forces between dissimilar molecules. When a chemical drum is emptied, there is often some surface wetting inside the drum. Sometimes chemical drums are reused to hold different substances. To keep different chemicals from mixing, the drums are often rinsed after they're emptied. Then they're allowed to dry completely before they're refilled. The next characteristic of liquids we're going to look at is called capillary action. If we place a tube into a container of liquid, the liquid tends to rise in the tube. The liquid level in the tube is higher than the liquid level in the container. This is the result of capillary action. As with wetting, capillary action is explained by the adhesive forces between the liquid and the tube. These adhesive forces actually pull the liquid molecules up into the tube.